All right, so last time we talked about a new mathematician, at least new to the subject we're talking about, which is Hamilton. And Hamilton circuits is what we're specifically talked about, whereas back in 15.2 we were talking about Euler circuits. And Hamilton circuits, in fact, let me go back to the first slide to remind you what we were coming from. This is a circuit in a graph that visits each vertex exactly once, returning to the starting vertex to complete the circuit. This is different than the Euler circuits. Euler circuits visit each edge or go along each edge once and then return to the starting point. So in Hamilton circuits, we have items. All right, it's going to flip to the next slide, I'm just sure of it. This probably sounds really funny if you look at it on YouTube because it shows that I'm already there and there's somebody out there saying, what is she talking about? Because they don't see this differently. Okay, there we go. All right, Hamilton circuits for complete graphs. So do you remember what a complete graph is? Talked about that. What's that? It's one component that's connected. So it's got more to it than that. It is a connected graph, though. With an edge, right? Yeah. So every vertex is connected to every other vertex with an edge. There was different ways we had of determining that. One is simply to just check every vertex and make sure that it's connected to every other vertex. Another way to do it is to count the degree of every vertex, make sure it's one less than the number of vertices in the whole graph. And then there was another option as well. I'm blanking on it, but those are two of the two options in as well. With Hamilton circuits, we want to talk about when a circuit is considered the same. And Hamilton circuits are considered the same when they differ only by their starting point. And if they just differ by their starting point, they're considered the same circuit. And I'm going to give you an example based on the last example that we did before we left class last time, but let me give you a chance to write this down first. Okay, our last example, we had a circuit. It was this one at the middle, part B. Do you remember this circuit right here? If we had taken that Hamilton circuit and instead of starting at A, we actually started at E, and we went E, C, D, B, A, and then E. Whoops. That would be considered the same Hamilton circuit as the original one we did. Okay, it's the same pattern, we're just starting at a different place in it. And you guys actually, at least I don't know about everybody, but there is a real common thing where people do this. Have you ever been a part of, or have you ever known someone who's been a part of a, they usually call them a scramble, a golf tournament scramble? What they'll do is they'll have however many teams, and there can be no more than 18 teams to make it work. And so a golf course has 18 holes, and they'll form 18 teams, and every team starts at a different hole. And so they do all 18 holes, they do them all in the same order, but you may not start at hole number 1, you may start at hole number 4. And so in order to make that work, we can't have everybody showing up at hole 3 at the same time, so we've got to all be going in the same order, but we start at a different place. So a golf tournament scramble has this sort of a process to them. We also want them all to play every hole in order to be able to compare them. So. All right, so we're going to determine on this example whether or not the graph has a Hamilton circuit. The first question we can ask ourselves is it complete? Because if it's complete, we know it has a Hamilton circuit, right? So the first question you should look at and answer for yourself is this a complete graph? This is not complete. That doesn't mean it doesn't have one, but it does mean we can't use that fact. This is not complete. Why? Yeah, because there is no edge UV, or you can say it how you guys do with the idea of them not being, an edge not connecting U to V is fine too. Now, if we take a look though, that doesn't mean there's not a circuit. Okay, it just means that it wasn't complete, so we aren't for sure assured that there's a circuit. So we'd like to try and see if we can find one. So we definitely have to start at either x, t, or w if there is one. Why?
The highest degree.
They have the highest degree. It isn't just the highest degree issue, though. There's something else. Typically speaking, we got to have an even number of vertices in order to an even number of degrees to get back to that point, right? So what happens at T, U, and W, sorry, T, V, I didn't say it right again, T, X, and W is that those are all even degrees, right? The degree 4. Okay, so let's take a look. Let's start at one of those. Somebody pick one for me. X. All right, where do you want to go after we visit X? We have to visit every point, right?
T.
You want to go to T. Okay, so we're going to go from X to T. Then what? U. All right, where's next?
W.
W. And then V. And then X. So we found a circuit, right? It's a Hamilton circuit. It didn't use every edge. It doesn't have to. It's not an Euler circuit, right? It's a Hamilton circuit. But it went to every single vertice. So this is what happens when I go shopping. I want to go to every single particular point, but that doesn't necessarily mean that I have to go in a specific order. So just because we wrote down X, T, U, V, W, W, V, X doesn't mean there aren't others, right? There are other Hamilton circuits, and you can see that there are many different correct answers written in parentheses there. Okay, we're going to do another example. It says determine whether a Euler circuit, a Hamilton circuit, or neither would solve the problem. Okay, so we've got an example. I gave you an example of a Hamilton circuit a little bit ago when we were talking about a golf tournament scramble. The vertices of a graph represent the places where the paths in a botanical garden cross. Okay, so this isn't the overlaid ideas of the highways in Texas, right? Every time they cross, it's really a vertex. That's what this says. Did you guys catch that? Okay, so these are actually the sidewalks crossing on the ground, okay? And then it says the edges represent the paths, that is the sidewalks. A visitor wants to walk along each path in the garden exactly once, returning to his starting point when finished. Is that an example of an Euler circuit, a Hamilton circuit, or neither? That is Euler. What is it that makes it Euler versus Hamilton? It's the paths or the edges. I mean, they're talking about paths like sidewalk path, right? But it's the edge issue. The edge issue is an Euler circuit issue. A Hamilton circuit issue would be the points if they wanted to visit every particular viewing point in this botanical garden or whatever. That would be a Hamilton issue. So this is Euler. Euler circuit. All right, so you might want to know, I mean, I told you on the last one right here, this example, that there's lots of other choices that could work. So you might be led to wonder, well, exactly how many choices are there? And we can at least answer that when it's a complete graph. Okay, so when we have a complete graph with n vertices, okay, so however many vertices we have, then we have n minus 1, and then there's an exclamation point Hamilton circuits. Have you seen that exclamation point notation before? Raise your hand if you have. Okay, most of you haven't. It's okay. Let me talk then a little bit about what that notation means. All right, so when you see an exclamation point notation, I'm just going to use it with n for the moment. I know that's not this particular problem. That's okay with me. If you have this particular notation, this means you take that number and you multiply it by a number 1 less than it, and 1 less than that one, and 1 less than that one, all the way down until we get to 3 times 2 times 1. This is actually not called an exclamation point, as you might have imagined, because that sounds a little bit too not mathy, doesn't it? Surely there's another name. It is. There's another name. It's called factorial. So in factorial is how this is read. I promise the 2 times 1 is going to come up in just a minute because it's on my screen. So in factorial is n times n minus 1 times n minus 2 times n minus 3 times n minus 4, however many you need until you get all the way back down to 1. So if you have a really large number, obviously this could take a while. I don't want to do 24 factorial. And 24 is not even that big. 24 times 23 times 22 times 21. And what will happen if you try to do numbers that are too large is that your calculator will spit back at you something that looks like scientific notation, because the numbers get very large very quickly. Okay? Some of your calculators probably have a factorial button in them. Okay? Some of them probably don't. So we've got to be able to work with this as though we don't have the factorial button. If you want to use the factorial button to check a solution, that's of course fine. So this actually tells us that when we have an in-circuit graph, then we have n minus 1 factorial ways of creating a circuit. So we have n minus 1, which is n minus 1 times n minus 2 times n minus 3, all the way down to 3, 2, 1. So we always end at 1 no matter where we start. Okay, so the first issue I want to do is simply let's find a factorial. Okay, so the first example that you see on the next example in your paper is we're just going to find 4 factorial. So somebody tell me written out, what does 4 factorial say? What is this? Right, it's 4 times 3 times 2 times 1. And I expect you to write it out. Okay, you're going to write out 4, 3, 2, 1. You're going to write that out. Then you're going to multiply it. What is 4 times 3 times 2 times 1? 24. Okay, so what this tells you is, in terms of our graph, and we're going to come back to this particular example in a moment, it tells you something about the number of Hamilton circuits within a complete graph. Okay, so for example, let's just say you had 10 vertices. That would be like a decagon. You've never seen a decagon before, but a 10-sided figure, okay, in some shape or form. And if we actually had it complete, that would mean every vertex going to every other vertex, right? So every vertex has 9 edges attached to it. Then what this formula tells us is that I have 1 fewer than 10, which would be the number 9 factorial ways of creating a Hamilton circuit. So if I were to do this, and this is not what I'm asked to do next, because it says leave answers in factorial notation, right? You see that in parentheses? As I sit here, I'm thinking a call to IT is in order, because even if they come and they look at it and it won't do this for them, it will fix it, right? And then all my screens will actually show up when they're supposed to for you. Okay, so pretend that it's underlined, leave answer in factorial notation, and pretend it says 9 factorial after that, okay? So if we were actually asked then to find all of the Hamilton circuits in a particular graph, we would have to multiply 9 times 8 times 7, 6, 5, 4, 3, 2, 1. We'd have to multiply all those numbers together. And would the number be large? Yes, it would, because 9 times 8 is already 72. I don't know about you, but I don't want to write all those different Hamilton circuits out. That sounds like it would take me a while and probably not be very enlightening when I was done, actually, either. And I might actually forget or miss one in the middle because I'd had to write so many of them. All right, so all right, let's pause this. See, I told you it was all there, right? Okay, so this is 9 factorial. If there's 10 vertices, there's 9 factorial. So we're going to do an example in a second of this, but we need to have a little bit more under our belt as to why it matters, okay? So the next item we're going to have a discussion of is what a weighted graph is. So a weighted graph is simply a graph with numerical values associated with each edge. Okay? So we're actually going to put numbers along our edges. So perhaps the numbers represent the time it takes to get from point A to point B. Maybe it represents the mileage it takes to get from point A to point B, because as you're well aware, going 5 miles through town takes a lot longer than 5 miles outside of town, right? So your mileage and your time may not necessarily go hand in hand all the time. But you've got some kind of a numerical association between the points along the edges, okay? And then a minimum Hamilton circuit, this is the Hamilton circuit with least weight. Okay? So I'm wanting to minimize the time it takes me to run my errands. or I'm wanting to minimize the amount of gas that I use because it's getting expensive. Actually, it's coming down a little bit right now. But for whatever, whatever you're trying to minimize, you're minimizing something that these numbers along the sides of the graph represent. Okay? So we're going to take a look at one. And we're going to use a brute force algorithm for finding that minimum Hamilton circuit. So here's the way it works. You choose a starting point. You can choose any point you'd like. Okay, so it doesn't matter which one it is. Because we're going to be dealing with, well, I'll show you in a minute. But we're going to list all Hamilton circuits that begin at that point. Okay, so we're going to start with that point, and we're going to list them all out. Which means that the graph can't be very big because I'm not going to list this out forever. All right, in fact, I'm about to do for you the largest one that you will see. You won't see anything bigger than the one I'm going to do. Okay, we're going to do the most time-consuming, is the word I want, most time-consuming one in class. Then you're going to find the total weight of each circuit, and then you're going to pick one of them, if there's more than one, there may be more than one, but one of them that has the least number associated with it, the least possible weight. And again, all of this is being done for a complete graph, actually. Okay, at least, I shouldn't say it that way, but we're going to see a complete graph used, which has the most possible ways of having these circuits. That's what we're going to see. All right, you guys ready? Okay, so this is going to show up at some point. There it is. This is actually a little bit messier than your paper looks, just because I have more control when I type than I write. One of the things to be aware of when you're seeing this is that this 15, 15, 13, 13, 21, this is actually this whole length 21, right? There's not another stopping spot in between. I know there's overlays, but again, imagine, like overlaying highways or something like that. This whole length is 13 and so forth. So you actually really do have numbers on every single edge of this picture. Does everybody see that okay? Okay, good. Now, we're going to start at point G just because it's at the top, not because of any specific reason. You can start wherever you'd like to start, okay? We're going to start with G. Now, somebody tell me for the moment first. Yes. Is this a complete graph? Yes, it is. There are 5 points in the graph, right? 5 vertices. And every vertice has 4 edges attached to it. Yeah, it's complete. So coming back over here, provided my screen will switch with me, I have a complete graph, right? One more screen. I have a complete graph. It has 5 vertices. How many Hamilton circuits will it have? 4 factorial, right? Right. Because this says if I have n vertices, I have n minus 1 circuits. So if I have 5 vertices, I will have 4 minus 1 factorial circuits. So this is 4 factorial. I'm sorry, 5 minus 1, which is 4 factorial circuits, right? What was 4 factorial? 24. We're going to write out 24 different circuits. How excited are you? Okay, how about this? None of yours will be this big on your homework. How excited are you? Yay, that's better. Okay, all yours will be smaller than this one, right? This is the biggest one there is. Okay, so we've got 24 different circuits that we're going to write out. That's what we're going to do. And we need to start at point G. Well, we're going to start somewhere, and I picked point G just at random. So we're going to start here at G. As I write my circuits, I'm not going to put the lines between them just because that's going to be on all of them, right? So I'm going to start at G, and then I need to know where could I go next? What's my next? What could be my next option? C. Okay, I could go G to C. And then what could I do? D. Okay? All right, so you want to go all the way around? All right, G, C, D, F. Did I miss one? E, F, rather. G. All right, so this is one circuit that I could have done. I contend that I also could have started another time with G, C, D. And I could even, then I have to pause, right? G, C, D. I can't go to E next and not get F, G at the end. So what could I do after I did G, C, D? What other choice could I make? F, D, G.
F, E, G.
Oh, did I write the wrong one? Sorry.
Well, you,
Oh, because it's not showing up. I said the wrong one for sure. Okay, so if I go G, C, D, these are the only two things that could happen, right?
right.
So far, so good. All right, what if I went just G, C? What could I do after after C instead of going to D?
F.
I could go to F, and then what?
And then you can go to
E, D, G.
Afterward.
You know how the first time how we went around?
Mm-hmm.
If you were to go backwards, would that be a different circuit or the same one?
It will be a different circuit because the order that we're going in is different. It's not the only time it's the same circuit is if the order starts at a different location, but it's still going the same direction. Yeah. So again, imagine like the golf tournament, right? If one of them goes holes 1 through 18 and the other one tries to go backwards, we're going to run into each other at some point, right? So, yeah, it would be different. We'll come to that one in a minute too. Is there another GCF that I could do? I bet there is. DEG. Okay. That should be all the GCFs. Sounds like I'm talking about greatest common factors like in the last chapter. So I did GCD, I did GCF. Is there another GC I could do? GCE. Sure, why not? Okay, so if I did GCE, then what do I have? What's left? FDG. There should be another GCE though, because there's been 2 of every one that we've started with. Sorry, it's not showing up. Look, there they are, really fast. Okay, GCE, what's next? DFG. Wow, that's 6 of them. Okay. GC, is there another GC? Or did I do them all? I think I did them all too. All right, so there's no GC left, so I'm done with the GCs, and that sounds like your cafeteria. So let's do another letter. What else could we do?
Wait, I have a question.
Mm-hmm.
Why didn't you go to GF?
I'm going to next. Well, I'm going to do something. These are the only GCs. We need to do something else besides GC now.
So I have a question.
Yes.
Would you then, well, that doesn't make sense, like, we had 6 for GC. So wouldn't there be 6 for GC, or GD, I mean? And then 6 for GE and 6 for GF?
Well, let's take a look and see. I'll move these to another screen because I need more space on the screen I'm on. I meant to cut it though. Okay. So let's do another one. G, what did you say? F? This was the backwards idea that Tori had. So if we do GF, what can we do next? Can we go all the way around? EDC, G? G, F, E. I'm sorry, what was your question mark again?
It's going to be the same pattern from G to F is what he's trying to say. That it's GC. 6 pattern is going to be linked into 4 different groups. So it's going to be 24 different
Yes,
categorizations.
it will. Is that what you're saying, Mark?
I think so.
Yeah, I mean, we have 4 different letters that can come after G, correct? Because there's 5 letters in this graph. I mean, there's 5 vertices. So we got, in fact, let me go over here so they show up. Oh, look, they're about to show up there. There were 6 of them that started out GC. There will be 6 of them that start out GF. There will be 6 of them that start out GD, and 6 of them that start out GE.
But not, oh, yeah.
And that's it, right? And that should be my 24.
Well, but, okay, so how come you wouldn't like then also go starting with another letter?
That's a good question. Come back over here.
You can, start at point G.
But like starting at point F?
Back up on the very front page of your notes, even though my screen's not showing it up there for you.
Point want to make things more difficult.
No, no,
so-
there's a better reason, Damon. Hang on just a second, okay? Remember there was a thing on the very front. Flip to the front of your packet if you have it, or look on somebody's who doesn't have it. Screen's not showing it. It's not showing anything now. Hang on. All right, so we were working on the different orderings of this Hamilton circuit, and we had G, F, E, C, D, G was our next one. Those are the only ways we can do G, F, E, so then we're going to do G, F, and consider a third possibility. So G, F, D, we could do C, E, G, or we could do G, F, D, and we could go with E, C, G. Next we can do G, F, and we've done E next, we've done D next, so we need to do C. So C, D, G, or C, D, E, G. And these are all the different ways we can start out with G, F. And so let's put these over here on this slide now. So we have half of the ones we're looking for, because there are 12 of these, and we should be having 24 when we're done, since I have 5 vertices. 1 less than 5 is 4, and 4 factorial is 24, as we've done before. All right, so we've looked at GC, we've looked at GF, now we're going to look at GE. All right, so we're going to do GE, and let's do GED next. So GED, F, C, G, which means then we also have GED, C, F, G. We've got GEC, D, F, G, and GEC, F, D, G. And then there's GEC, oh, not C, sorry, GEF, C, D, G, and GEF, D, C, G. And that's 18 now. Our last set are going to be the GDs. So we have GD, F, E, C, G. We've got G, D, F, C, E, G. We've got G, D, C, E, F, G, and G, D, C, F, E, G. Then finally our two are G, D, E, C, F, G, and G, D, E, F, C, G. Alright, so what we next need to do is we need to figure out what the Hamilton circuit weights are for each of these. And I'll just do a few of these to give you an idea of how they would work. And we'll do that based on the picture that we've got next to this. So I've got to go G to, and we'll do the ones that are on this screen actually. So I've got G to D, so that's this piece, and that's 13. And then I need D to F, that's this piece, that's 21. I need to E, which is 17, over to C, which is 15, and then back to G, which is 10. And if I take a look then at my particular picture, I have 13, 21, 17, 15, and 10. And if I add those together, 13 plus 21 plus 17 plus 15 plus 10, I get 76. So So the weight of this first one, in fact I'll use yellow, this one is 76. So let's try the next one. We're going to go GDF, which is all the same still, so GDF. So that's again 13 plus 21. And then I'm going over to C, which is 15, down to E, which is another 15, and then back up to G, which is another 13. And let's see here. That gives me 77. We'll do one more just to give you an idea of how this is working. This is GD, again, 13. C's next, so that's 12. From C we're going to go over to E, that's 15. From E we're going to go up to F, that's 17. And then from F we're going to go back up to G, which is another 15. And that ends up being the smallest one we've seen so far at 72. So we would do all of this for all 24 of these. We would check their weights, and whichever one or ones have that minimum weight, that would be a minimum Hamilton circuit. And we will likely have more than one of those. All right, another idea, however, is that, as you can imagine, if I had, instead of just 5 points, but I had 6 points, and I wanted to do 5 factorial, 5 times 4 times 3 times 2 times 1 is 120. And I don't know about you, but I don't want to do 120 of these circuits. This sounds like a really big task, and maybe a little bit more than I can bite off, and I just don't want to bite off that much. And so I want to talk about an efficient algorithm. An algorithm that does not take a computer much time is considered an efficient algorithm. And an approximate algorithm is, again, one of these efficient algorithms, one that doesn't take the computer much time, and it gives reasonably good solutions most of the time. So it's not perfect, it's not 100% accurate, but it's efficient and still reasonably good most of the time. So let's take a look at one such algorithm. That is the nearest neighbor algorithm. The nearest neighbor algorithm says the following. We're going to choose a starting point, and just for the moment we'll call that point A. And then we choose an edge of least weight that is connected to A, and we go down that edge. And then at each vertex we come to next, we repeat that process of choosing the least edge from among those we have not yet visited. And then we repeat step 3 until we have visited all vertices and return to the starting vertex. And I have an example for us to take a look at. So we're supposed to start at F, which has, which is up here in this corner. In fact, let me put in the points that are so missing. There we go, that's better. All right, so we're going to start up an F in the corner, and we're supposed to choose the least path. And that edge actually would be this edge 2. So we would come down here like so. So we would go up there, and then from H we have 2 paths. We can go up to I and go 4. We can go over to G and go 7. So we're going to go up to I since it's of length 4. And then we're going to go from point I over to either point F, which would give me 5. But that's a problem because I would then complete my circuit, and I need to go to all the points. And also because this point 3 is actually a smaller vertex, or smaller edge length. And then we would go up to point F along this side 6. So I go from 2 to 4. Alright, so I went F to H to I. In fact, let me write it like this. F to H, which was 2 points, or 2 value, to I, which was worth 4. After I came down to G. That cost me 6. I'm sorry, it cost me 3, and then back up to point F, which cost me 6. And if we take 2 plus 4, that's 6 plus 3 is 9 plus 6 is 15. So this is a 15 length, or valued path weight. And then we can do the same thing with point G. So we'll start with point G, and the least path, of course, is to go from G to I. So that G to I costs me 3. From I can either go over to F at 5 or down to H at 4, so I'm going to go down to H at 4 since it's less. After H, I have to visit my last remaining point, or my last remaining curve, which is F, which is giving me 2. And then from F, I have to go back to G, and that is 6. So we add 3 plus 4 is 7, plus 2 is 9, plus 6 is 15. And these do not have to end up being the same value, but you can see that in this case they were.